Problem 2 for the practice problems asks us to find the activity of a 4.6 gram sample of cesium-137. So activity is equal to the rate constant times the number of particles that we have. So A equals K times N. So activity, if we want it in becquerels, it's going to be in disintegrations per second. Okay, so our rate constant here will be in units of seconds minus 1, and this here is number of particles that we have in the sample. And so that's what we're going to use to solve for this. Okay, so we're going to take our 4.6 grams of cesium-137 and we're going to find out how many particles that is. Okay, so we have 4.6 grams of cesium-137. Okay, so we're going to start there. So 1 mole of cesium-137 per every 137 grams of cesium-137. Okay, so for this part here, I did not look at cesium on the periodic table. The mass number gives you very, very close, within a few tenths of a gram of the molar mass. So again, I did not look at the periodic table. On the periodic table, cesium here is 132. So that's the average of all the cesium. We had specifically cesium-137, so it's perfectly reasonable to estimate that as 137. Okay, so again, if we need now the number of particles, we're just going to multiply that by Avogadro's number. So atoms per 1 mole. Okay, so this will give us our number of cesium atoms at 2.02 times 10 to the 22 atoms. And we just solved for N in our formula above of activity equals K times N. Okay, so now to get our K, we need to take the half-life given to us in the problem, turn it into the rate constant, and then turn it into the proper units of per second. Okay, so we have 30.2 years. So K is equal to the natural log of 2 over t1/2, which equals the natural log of 2 over the 30.2 years. Okay, so when we solve that, we get 0.02295 years minus 1. Okay, so we want to turn this into the proper units for our formula. So because we're solving for disintegrations per second, we have per year here. So all we're going to do is turn per year into per second. Okay, so we're going to do some conversion here, and again turn this into a little bit of seconds. So 1 year, I'm going to take this and put it down here. Okay, so 1 year per, we'll say 365 days. So next, 1 day per 24 hour. And then finally, 1 hour per 3,600 seconds. Okay, so when we solve for that, we get 7.28 times 10 to the minus 10 seconds minus 1. Okay, so we've turned our rate constant in units of per year time to per seconds time. So now to finish this up, we're going to go back. We now have N. This is our K. So we're going to take our N and our K and put it into our activity formula and just multiply. So now we have activity equals our N, 2.02 times 10 to the 22 atoms times 7.28 times 10 to the minus 10 seconds minus 1, and this will give us essentially the atoms that can disintegrate per second. So when we do that, we get 1.47 times 10 to the 13 becquerels. And my dog says that this is correct. Do you hear how excited he is? Okay, so here is our answer again. Units of K in seconds minus 1, and we solved here for the number of radioactive nuclei here. So particles here again, that would be radioactive nuclei. Okay, so radioactive nuclei times the rate constant gives us the activity. Okay.